Today, in our classification series, we're going to talk about a regression technique. Welcome to this video on classification. My name is Kevin Fiesel, and I am the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. Today's video covers one of the many interesting classification techniques we have available to us: logistic regression. Logistic regression is a regression technique that... Okay, let me start over. Logistic regression is a classification technique that regresses against... Okay, it's time for me to engage academia mode. As a quick warning, there will be some math here, but I am going to keep it a bit lighthearted in nature because that's typically how I roll on this channel. If you want to see logistic regression in a lot more detail, I do have a 3-hour course that is available for sale through the EC Council. I put it together about a year or so ago. It is not a free course, but if it helps you sleep better at night, I'll probably never see a dime from the course purchases due to the royalty structure. Nonetheless, I'll have a link to it. Anyhow, let's get into the real debate. Is logistic regression classification or regression? Allow me to illuminate you. The smooth-brained answer is, logistic regression is a regression algorithm because it's literally got the word regression in the name. But that's not going to be good enough for us because this world is full of lies.
There's only one thing I hate more than lying: skim milk, which is water that's lying about being milk.
That leads us to our midwit, who says that clearly logistic regression is not a regression algorithm. It's a classification algorithm in regression clothing. We primarily use logistic regression as a classification technique because we have a clear bifurcation with values driving toward either 0 or 1. But no, as you dig in deeper and research the mystery of logistic regression, you find out that logistic regression is indeed a regression algorithm. It just happens to work well for classification because logistic regression is built on top of probabilities. Well, okay, if you want to get technical here, logistic regression is built on top of logits, which are log odds ratios, but I'm getting a little ahead of myself. Let's first talk about the 6 key assumptions behind logistic regression. The first key assumption is that we have a binary response variable: yes or no, good or bad, 1 or 0, or even 1 or -1. The labels themselves don't matter, so long as we have exactly 2 of them, which sounds a lot like what we need for classification. The next thing we need is a set of independent observations. An observation, by the way, is a more proper term for records in our dataset. Our observations should be unique, in that we're not just copying the same observation over and over. If we do that, we can skew the results in a logistic regression. The third assumption is that there is no severe multicollinearity. Collinearity, by the way, is when things move together in a linear fashion. If I have 2 features, one of which is simply a multiple of the other, these 2 features are collinear, and we see multicollinearity. And that's a problem for logistic regression because the algorithm won't know how to apply weights to how important a change in one value is because the other feature changes by the same percentage amount. So we need our features to be at least somewhat independent. There can still be some level of correlation between features, but they can't be quite so closely tied together. The fourth assumption is that we have no extreme outliers in the dataset. Logistic regression can fail when we have a couple of outliers, especially if they all go in one direction. Imagine in your mind an S-curve or a sigmoid function, or how about I just show you one? This is essentially what we're generating with logistic regression. If you have no outliers in the dataset, you'll end up with a range of values on this curve, but they'll end up being distributed close to 0 and close to 1. The problem is, if you have even a few extreme outliers at the top end, it'll push all of the values that normally would have clustered around the 1 further down the curve, to the point where either we have difficulty at judging whether these values should be 0s or 1s, or even going so far as to misapply them as 0s. This means we're going to want to ensure that the data fits the same distribution and comes from the same data source. The fifth assumption around logistic regression is that we have a large enough dataset. If you only have a few records, logistic regression likely won't have enough information to give you a solid answer, so you need a good number of observations to have confidence in your answer. What's a good number of observations? Well, one rule of thumb is that you should have at least 10 cases for the least frequent outcome for each explanatory variable. Just as a hypothetical, let's say that we have 6 explanatory variables, and the probability of the least frequent outcome occurs 15% of the time in our data. In that case, we can take 10 times 6 and get 60. Divide that by 0.15, giving us a minimum of 400 observations. If we have 1,000 observations, we're in good shape. If we have 350, it's iffy. If we have 20, we don't have enough data. Our final assumption is that our features have a linear relationship to the logit of the response variable. That's because logistic regression is linear regression wearing a disguise. But wait, we see that word logit again. I guess it's about time I explained the term, huh? To do so, let's first talk about probability. Probability answers the question, how likely is an event to occur given the information we have about it? For example, suppose I have a fair 6-sided die. Let's not quibble about how I know it's fair. We'll just take it as given the die is fair. What I mean by this statement is that there are 6 possible sides, and each side is equally likely to show. Therefore, the probability of any particular side showing after I roll it is 1 divided by 6. Put more specifically, the probability that a 2 will show is 1 divided by 6. The probability that a 4 will show is 1 divided by 6. The probability that a 5 will show? Yeah, same thing, 1 over 6. Now that we know that the probability we get a 5 is 1 over 6, let's convert that to odds. The formula for what we call the odds ratio is p divided by the quantity 1 minus p. Put more specifically, the odds that we will roll a 5 on our fair 6-sided die is as follows. P is equal to 1 over 6. Thus, we have the quantity 1 divided by 6 divided by the quantity 1 minus the quantity 1 divided by 6. Simplifying terms a little bit, we end up with the quantity 1 over 6 divided by the quantity 5 over 6. The over 6's cancel out, leaving us with odds of 1 over 5. In the US, we most commonly hear odds like this described as something like 5 to 1 against. Incidentally, you might be wondering why we even care about odds when it's just another way of describing probability. Well, the answer is humans have a hard time working with small probabilities. Let's say that I have the 2 probabilities here and I'll show them on the screen. So these are definitely probabilities, and we can say that one is more likely to happen than the other, but it's really hard to wrap our minds around these numbers. But if I tell you that one of them is 20,000 to 1 odds and the other is 25,000 to 1 odds, the numbers actually work out better in our heads. The 2 concepts mean the same thing, and you can do the math to switch from one to the other. So it's safe and fair to use either approach when it makes sense and your audience understands how the 2 relate. Now that we have this idea of odds, let's talk about what this gives us. So this is an example of an odds ratio using the MT-CARS dataset. In this example, I'm interested in seeing how horsepower relates to the likelihood of having an engine with V-shaped cylinders rather than straight cylinders. To do so, I'm plotting the odds ratio of having a V-shaped set of cylinders on the y-axis and horsepower on the x-axis. We can see that for values under approximately 150 horsepower, we are very unlikely to have V-shaped cylinders. As we move above 150, we get more and more likely, exploding by the time we get to 200 horsepower, so that near the end of the curve at 240 horsepower, we are extremely likely to have V-shaped cylinders. But this graph is hard to read because we are plotting an exponential curve. And the trick to viewing exponential plots is to plot a log linear relationship. In other words, the relationship between the odds ratio and our explanatory variables is log linear in nature. If we plot the log of the odds ratio, we get a straight line. And that leads us to the definition of a logit, the log odds ratio, or the natural log of p divided by the quantity 1 minus p. And thus, what we're really doing with logistic regression is performing linear regression using our log odds ratio or logit. Logistic regression is a regression technique. one that happens to be effective for classification. And it turns out the smooth-brained had it right the whole time. There's a whole lot more we could talk about with logistic regression in terms of sigmoid functions, loss functions, and so on, but that's something you'd have to go to the course to get. Now let's go to the demo notebook and see how we can run a logistic regression. This is the notebook we'll use for logistic regression. I'll start with a setup that should look familiar to you if you've been following along in this series. We pull in NumPy and pandas, as well as some scikit-learn functions and modules. Our algorithm comes from sklearn.linearModel, and we instantiate it as a classifier. We set the max number of iterations to 1000 to prevent a warning message about convergence, and I'll give you a hint as to why that shows up as we get to the data. The dataset we'll use is the same campus recruitment dataset we used for k-nearest neighbors in the prior video. I'm hurrying through the prep work for this because it's fairly simplistic. We'll read a CSV file with headers. The label column is status, which tells us whether a college graduate ended up with a job post-graduation or not. There are two additional columns we'll drop from the set of features. The first is SL number, which represents the student number. This is a unique number, so it won't be of any help to us in classification. The other column is salary, which is the salary a person received in their postgraduate job placement. That's not something we would know before the fact, so we'll want to drop this column as well. Taking a quick look at our dataset, we have a mixture of categorical and continuous features. In the prior video, I talked a bit about these, but for the purposes of following along today, we just need to know that this is what's available to us. Now, let me ask a question. How many observations do we need? As a quick reminder, I mentioned in the classroom segment that logistic regression is a fairly greedy algorithm in terms of data requirements. Our rule of thumb is that we want 10 times the number of features and take that quantity and divide by the probability of the least common occurrence of some feature. Let me show you a practical way of figuring out this value. In my dataset, I have a set of categorical features and a set of continuous features. I'm going to skip the continuous features for the sake of simplicity, but I should note that a thorough analysis would incorporate these features as well. And the way that I would likely incorporate them is to bin each one of the continuous features. Then I could build a histogram and see how frequently we see results in each of the resulting bins. But because we're doing things a little loosey-goosey here, I'll focus on the simpler example with categorical variables only. Here I have a loop that prints out the unique set of values for each categorical variable. We can see that these variables take on one of either 2 or 3 values per variable, so that's actually a really good sign. If we had some categorical variable with 100 separate features, that'd be really bad for us given that we only have 215 rows in our entire data set. Let's now take this same set of features and print out the value counts. This function, value_counts, gives us each value for a given column as well as its frequency of occurrence. For example, in our 215 entries, we have 139 males and 76 females. We have 116 people in the central area and 99 outside of it. As I scroll through here, there are only 2 areas where I'm a bit concerned. Those are school and degree type. We have 11 people from the School of Arts and 11 people who did not have a degree in either communications and management or science and technology. 11 out of 15 is approximately 5%. So the probability of our least occurring feature is 5%. Thus, I can take our rule of thumb, 10 observations times 11 features, which is 110. Divide that by 5% and we get to 2,200 total observations that we would like to see. In reality, we have 10% of that. In a normal case, this would be a fairly scary proposition, but we do have one thing going for us. Most of the features are fairly well distributed, so we're at higher risk for those 11 School of Arts graduates, but we do have good representation for the other 204 students. I will note, before I continue, that our training dataset will only be about 150 rows. This can also lead to a problem with convergence given the solver method we're using by default for logistic regression. And that's the reason why I set the max number of iterations to 1,000 when I defined the classifier object. That's the third or fourth sign that we probably need more data to make the most use of logistic regression, but nonetheless, the show must go on. Just as with our k-nearest neighbors analysis, we're going to one-hot encode each of these categorical variables and splice them together with numeric features. Doing so, we'll get 215 rows of 21 columns of data, and I can see the data frame in all of its glory. Or at least as much of its glory as Jupyter will let me see by default. When it comes to our label data, I'll use the same label encoder that I used for k-nearest neighbors, transforming placements to 1 and non-placements to 0. Then I'll split the data into training and test data sets using the same random state as before to make cross-comparison easier. I have a training data set with 150 rows of data exactly. Now let's fit the logistic regression. Just like k-nearest neighbor, logistic regression is a deterministic function, so I don't have to worry about random states or anything of the like here. Let's take a look at the results. We can see an accuracy of 84.6%, which is good. It's a little better than k-nearest neighbors and a little worse than XGBoost. I can dig further into the confusion matrix and see where it does well and where it falls short. If we look at the table below my classification report, I've put together the values for the 3 algorithms that we've used so far against the campus recruitment dataset. K-nearest neighbors has done the best at identifying which students got placements, but it was also the worst at identifying which students would not receive job placements. XGBoost was ever so slightly better than logistic regression at both, but we're talking about a difference of 1 person in each direction, so I'm not sure how that difference would hold up under a larger sample. Despite logistic regression shouting from the rooftops that I really need more data, it certainly acquitted itself well in this scenario. And that was logistic regression. Despite the confusion about whether it's a regression or a classification algorithm, it typically does quite well at classification. In the next video, I'm going to talk about the skim milk of the classification world, at least in terms of its name. We'll have links and show notes in the description below, and until we see each other in the next video, take care.